Stokes' theorem is essentially what you get when you take Green's theorem about a region in the plane and lift it out of that plane. So for Green's theorem, we'd have a picture something like this, where we have some region D with its boundary C, oriented in a positive fashion, and a double integral over the region D corresponding to the line integral around the region C, around the curve C. For Stokes' theorem, instead, we will be dealing with a section on a surface. So we have here some surface somehow oriented in three-dimensional space. That surface does have, because we're looking at a bounded region on that surface, it does have an actual boundary curve, and we're going to relate a double integral, or really a surface integral, over the actual surface S to the curve around that section. We do need to be careful when we're dealing with orientations. So when we're dealing with Green's theorem, we basically kind of didn't really talk about the orientation of what's going on inside the double integral. We pretty much just took the orientation of having the normal direction being out of the plane. Basically, we take our normal to just be k, where k is our third dimension that's sticking out of the xy plane, and that is always perpendicular to this region D. And that didn't really need to be talked about when we were just talking about two dimensions. But when we do talk about a surface, we do need to actually have a normal direction to talk about. So in this case, we'll say that normal direction is something like this, and of course we'll call that n. So our unit normal, or our orientation, is n. It's the vector n. Once we have that orientation, we can use that orientation to define the orientation for the curve C. So C is defined by its tangent vectors, the direction that we go around here. When we were talking about Green's theorem, we oriented it normally in a counterclockwise fashion, but we specifically said that in case that we had any holes in the middle here, that we are always treating it as if the curve, or if D was always to the left of our orientation. Basically, we're imagining if we're a person walking along that curve, the D would always be to our left. When we're talking about a surface, we have to have a direction that we are facing, so we have to have a direction for our head. If our head is in the direction of the normal vector n, and we're walking along the boundary, now the surface is going to always be to our left. For Green's theorem, we just kind of had that thought that our head was always in the upward direction, the positive k direction. And we're going to keep that idea even if our normal direction can be something else. But we're going to use that normal direction for our surface to define where our head's going to be. And so that's going to be what we call our positive orientation for that curve. And with that, we are able to state Stokes' theorem. So for Stokes' theorem, we have S being an oriented piecewise smooth surface that is bounded by a curve, this simple closed piecewise smooth curve C, and it has positive orientation with regards to the normal, the orientation that we've chosen for the surface. If F is any vector field whose components have continuous partial derivatives on any region around S, so that we're able to actually talk about its derivatives, then the line integral of f around the boundary curve is equal to the double integral of the curl over that surface. Now keep in mind here, if we were looking at Green's theorem, if we basically have f is equal to pi plus qj, where we don't have an r component here, and p and q only depend on x and y. The curl, if you recall, is just going to have that third component. It's going to be partial of q with respect to x minus partial of p with respect to y times the unit vector k. And if you took this unit vector k, or you took this curl and took the dot product with the unit vector k, then k dot k is going to be 1, and we're just going to have this inside. That is the inside of Green's theorem. That's the integrand that we have in Green's theorem. Essentially meaning that Green's theorem is a special case of Stokes' theorem when we actually have our surface as part of our xy plane. Of course, proving Stokes' theorem in full generality is far outside of what we're able to do in this class. It is actually a pretty involved theorem. Instead, we're going to look at one special case, where the surface S is given as the graph of a function, z equals g of xy, over some region D in the xy plane. And we're going to assume here that g is nice enough to have continuous second derivatives. So that's not necessarily a requirement of Stokes' theorem, but we're going to have to assume it here for this version of the proof. So what we have here, we have some region D in the xy plane. We have some surface over D. This is our S. S obviously has a boundary curve C. And D itself also has a boundary curve, which, sticking with the way the book named it, we're going to call that C1. I wish they picked a different letter, but that's what they picked. We are going to take the upward orientation for S. So the normal direction has a positive z component. It doesn't have to necessarily be a vertical vector, but it has to at least be upward. So it could be off somewhere like that, but it still has a positive z component to it. Of course, down here in D, we have our actual vertical normal vector. Now, in the last section, we did have a formula for when the surface integral is actually of a surface is given by a graph. So here, if we're integrating over a surface z equals g of xy, then the actual surface integral is given as a double integral over the region D of this particular form. And that's what we're going to be using here. So, of course, capital F is pi plus qj plus rk. But when we're looking at Stokes' theorem, we're actually going to be looking at the surface integral of the curl. We want the curl of f instead of f itself. So we're going to have to take this f and the p, q, and r and replace it with the formula for our curl. Recall that the curl of f, where f is pi plus qj plus rk, has the form of the partial of r with respect to y minus partial q with respect to z times I. That's our I component. Our j component, we have partial of p with respect to z minus partial of r with respect to x. And then finally, our k component, this is the one that we see in Green's theorem, is partial of q with respect to x minus partial of p with respect to y times k. We're going to replace that in our formula here. So the surface integral of the curl of f dot ds is going to be the double integral over this d. We're going to replace the p here with this form here. I'm just going to use the minus sign to swap the order. So I'm going to take the partial of q with respect to z minus the partial of r with respect to y. That's going to be multiplied by the partial of g with respect to x. Then again, the minus sign here, I'm going to swap the order. We'll have the partial of r with respect to x minus the partial of p with respect to z times the partial of g with respect to y. And then finally, we get to just add in the r. We have partial q with respect to x minus partial p with respect to y. For now, we're going to actually leave this form alone. So we'll come back to this in a moment, but instead we're going to work with the line integral, and we're basically going to put it into this form. Maybe I'll actually do that on a separate page. So when we have C1, we can actually go ahead and parameterize it. This is the curve around D. We can say that x is equal to x of t, y is equal to y of t. Obviously, z is equal to 0 because we're working with a curve in the plane. Our t is going to go from some a to b. It is a closed curve, so actually when I put in a and when I put in b, I get the same point out, but I mean, they're technically different parts of the curve, different t's. If that is a parameterization for C1 with a positive orientation around D, then we can actually turn it really quickly into a parameterization for the curve C that's going around S. And even sticking with the positive orientation because the orientations for D and S are both upward. Essentially, we can attach to it, take those two as our x and y coordinates, but then attach to it z equals g of x and y to be our third component. Instead of z being 0, now z is equal to g of the x and y that we have. And that's going to be the correct orientation for the curve C. Now, when I actually take the line integral, I'm going to need the derivatives of these. So, well, I guess for x and y, those are just going to be the dx dt and dy dt. But for z, we're going to actually have to use the chain rule. dz dt, we're going to have the derivative of g with respect to x. Actually, that should be a partial derivative. So the first spot on g, we're taking the derivative of, but then we have to multiply that by the derivative of what's inside that first spot. Then we have to add that to the derivative for the second spot, for the g with respect to y, and then we have to multiply by the derivative of y with respect to t. When we actually plug all that in, we have the line integral over c of f dot dr. This is going to be the integral from a to b of, remember, f is pi plus qj plus rk. So we have p times the first component of f dotted with the first component of the derivative of r with respect to t, which is just dx dt. Then we have the second component of f times the second component of r prime, plus the third component of f times the third component of r prime. Of course, this is the one that we're going to have to change to involve g. So I'm just going to take dz dt and I'm going to replace it with that. Now, each of these terms does have either a dx dt or a dy dt. If we group those up, so I'll put all the terms that have dx dt first. So we have p plus, and we have r times the derivative of g with respect to x. That's times the derivative of x with respect to t. Then we have q plus r times the derivative of g with respect to y. That's times the derivative of y with respect to t. We have dt. And then, well, when we actually have this form, this is really just the integral of p plus r times the derivative of g with respect to x dt plus q plus r times the derivative of g with respect to y dy. Because that's what we do when we actually take this kind of a line integral over c1. We have the derivative of x with respect to t, derivative of y with respect to t, and we put a dt at the end. That's how we actually set up the line integral over c1. So we've taken a line integral over c, we've turned it into a line integral over c1. Now, since this is a line integral over c1, which is the positive-oriented boundary of D, we can actually use Green's theorem on this on this line integral. And remember, with Green's theorem, this turns into a double integral over D. We take the x derivative of our second component here. This is basically playing the role of q in the line integral for c1. Then we subtract the y derivative of our first component. And now we get to do some differentiation. I'm going to leave out the integral for now. I'm just going to work with what we have inside here. So now we just have our integrand by itself. And keep in mind that when we are differentiating, we have to treat the fact that p, q, and r are not functions of x and y specifically. They are functions of x, y, and z. They can have z's in them. But z is being treated as a function of x and y. So when we differentiate, say, q with respect to x, we're going to have to use the chain rule. Q depends not only on x and y directly, but also z, and z depends on x and y. So the derivative of q with respect to x not only includes the direct derivative, but also a derivative through z and x. But keep in mind, these are both derivatives of g. So the derivative of z with respect to x is really the derivative of g with respect to x. So I have to make sure when I differentiate here, I take that into account. So here, the derivative of q is going to turn into the derivative of q with respect to x, but also plus the derivative of q with respect to z times the derivative of z with respect to x, but I'm going to write that as the derivative of g with respect to x. Then we move on to the derivative of r times the derivative of g with respect to y. Of course, that is a product of two functions, so I will have to take the product rule of that. First, I'm differentiate the first, but that's derivative of r, which same here, just like with q. It depends on x, y, and z, which it depends on x and y. So derivative of r is going to be the derivative of r with respect to x directly, plus the derivative of r with respect to z, times the derivative of z with respect to x, but that is the derivative of g with respect to x. That's going to be multiplied to the derivative of g with respect to y. Now we take the derivative of the second part, so the r is still left alone. Derivative of g with respect to y, but then with respect to x, so we actually get a second derivative of g. So that's why we need to make sure that we do have second derivatives of g to be able to work with. But that's the derivative of g with respect to y, and then x. Now we move on to this part, which is very similar to what we have here, except now we're differentiating with respect to y, and we have p instead of q. I guess this is a x instead of y as well. But the form is going to be very similar. But we do have to make sure we have the minus sign here. So I'll subtract the derivative of p with respect to y. That'll be the derivative of p with respect to y directly, plus the derivative of p with respect to z, times the derivative of z with respect to y. We move on to a product rule here. In fact, we're going to have exactly what we have here, except with respect to y instead of x this time. So the derivative of r with respect to y directly, derivative of r with respect to z, and derivative of g with respect to y. That'll be multiplied to the derivative of g with respect to x. Finally, we have the r itself, but times the second derivative of g, this time with respect to x first, and then with respect to y. One thing that you can notice is that here we have a derivative of r with respect to z times the derivative of g with respect to x and the derivative of g with respect to y. Whereas here we have the same derivative of r, and then we have, well, they're in a different order, but the same two derivatives of g with respect to x and y. But this time it has a minus sign. So actually, this term here and this term here cancel each other out. Another thing you can notice here, these two terms at the end of both these lines, they look very similar as well. The only thing that's different about them is that we've taken the derivatives of g with respect to y then x, and x then y. But recall that since we are assuming that here that g has continuous second derivatives, not just that it has second derivatives, but they are continuous, then Clairaut's theorem says that we can change the order of differentiation. So these two derivatives are exactly the same thing. And therefore, when they're both multiplied by the same r, they'll still be the same thing, and we have a minus sign here, so they cancel out as well. So at least we got some terms canceling out, but we do have a lot of other terms. If we write all those out, and I'm going to also group them together corresponding to whether or not they have a partial of g with respect to x or partial of g with respect to y. We can see all the ones that have partial g with respect to x. Here we have a partial of q with respect to z. We don't have any more from there, but here we get a minus partial of r with respect to y. That's being multiplied to the derivative of g with respect to x. All the ones that have a partial of y, g with respect to y, that we get one from here. We get a partial r with respect to x. And here, we get a partial of p with respect to z. So that difference will be multiplied to the derivative of g with respect to y. Finally, we have two more terms that we haven't accounted for. We have this partial of q with respect to x, and we have a negative partial of p with respect to y. But that accounts for all 6 terms that survive the cancellations. But if we take a look at exactly what we have here, and I know there's a lot of stuff going on here, and it might be a little hard to just take it all in at a glance. But if we go back to the form that we had for our surface integral of the curl, this integrand here is exactly what we have here. And therefore, the integral of this form over d, which is what we're looking at here, is equal to the line integral of f dot dr. Which is exactly what we wanted to prove, that these two integrals are equal to each other. Now, of course, we've only done this in one particular case. If we have a parameterized surface, it still actually does work. It just takes a lot more effort to prove. And we're definitely not in a place where we could do that here. One last thing I want to go over before we end this video, though, is recall back in section 16.5. That was the section where we defined the curl and divergence. And one thing that we mentioned there was that if f is a conservative vector field, its curl is always equal to 0. Remember, the curl of any gradient is always equal to the 0 vector. So if f is given by the gradient of some potential function, its curl has to be equal to 0. And we mentioned here in this theorem that as long as we have the correct conditions on our domain, here they specify that it has to be all of R3. I did mention back then that we can actually generalize that a little bit more, though we don't really want to get too into that. But as long as the domain is nicely behaved and the curl is equal to 0, then f is also conservative, that it goes both ways in that case. Well, Stokes Theorem is what kind of gives us the key to actually showing that. Because remember, all the work that we did about conservative vector fields means that they're still connected to the idea of being path independent. That the integrals of f over any paths between the same 2 points will always be the same. That's true regardless of whether it's 2 dimensions or 3 dimensions. But what we want to show here is that if the curl is equal to 0, then that means that the integrals of f are path independent, and that will mean that f is conservative. So let's say we have any path from, let's say, point A to point B. So we have some path, let's call it, I guess we'll call it C1. We have the path integral over C1 of f dot dr. And we have another path that we'll call C2. Are these going to be the same thing? Well, I've drawn them here. These are actually paths in the three-dimensional space, so these can be quite different in terms of what they actually look like, depending on your perspective of it. But one thing that you kind of have to take for granted right now is that as long as we have our conditions, especially here that that our vector field is defined in all of three-dimensional space, is that we can actually find some surface between these two curves. There is going to be some surface here, which we'll go ahead and call S, that connects those two curves. So these two curves actually form a boundary of that surface. That's not a trivial fact. That's actually a pretty complicated thing to prove in of itself, but we'll kind of take it for granted here. This is kind of why we need to why we have to have these conditions on our domain, though. If there is, say, a hole that we couldn't bridge between these two curves, then this wouldn't be possible. Now, if there's just a single point, we could theoretically go over it. So we kind of have to have holes that are trickier to overcome. And that's why we don't really want to get into it right now. We had to develop some definitions in order to really put it clear what kind of holes are possible and what kind of holes are a problem. But as long as we can actually form the surface, of course, the integral over this entire boundary. Now, of course, the way I've drawn it here, I had to pick what normal direction I have for S. Let's assume it's the upward one. And then the positive direction around the boundary here would actually be to travel along C2 and then backwards along C1. We have to keep in mind those are that to go all the way around, one of those will have to be opposite. So we'll have the integral, let's say over the whole boundary is C. So C is the entire boundary. Of f dot dr, which is the difference between these two, essentially. We have the integral along C2, but then when we're going backwards, we have to treat that as the negative of the integral over C1. But this, because of Stokes Theorem, and the fact that we've already mentioned that it has to do with our surface in the middle, we can write this as the double integral, or the surface integral over S of the curl of f dot ds. But we're assuming here the curl of f is 0. So this integral has to be 0. I mean, the integral of 0, whether it's 0 as a scalar or 0 as a vector, is just going to be 0. that means that this difference has to be 0, that these two integrals have to be the same thing. So the integral over c1 of f dot dr has to equal the integral over c2 of f dot dr. And so, f is a conservative vector field. Its integrals over any curves are independent of which path we actually choose. So at least maybe you have an idea of why the curl is that good condition to check whenever you want to talk about conservative vector fields. Whenever you want to know whether or not you can get a potential function for a particular vector field. Now I'm going to go ahead and leave this video here. So we've gone through kind of a proof of Stokes theorem. We really haven't brought up too much. It's mainly all just about Stokes theorem. But in the next video, we're going to go through some examples of how we can use Stokes theorem to solve various problems, and even how Stokes theorem can simplify a lot of problems to be a lot easier than they were initially. So meet me there, and we'll get to it.